Okay, so today we're diving into a world where physics meets cybersecurity, right?
Yeah.
It's all about quantum communication protocols and how they use these really mind-bending principles of quantum mechanics to try and build super secure communication channels, something that's, more important than ever in our
Excellent.
digital world. And I think what's really driving a lot of the urgency behind this, as we explore in this deep dive, is that the way we currently protect our data, our classic cryptography methods, might actually be on shaky ground.
Yeah, you're absolutely right. And that's something that Yogo Schneeppert, the author of the essay that we're looking at today, really highlights, right? Quantum Communications Protokolle, Sicherheit der Zukunft. I mean, the future of security. That's what it's all about.
Exactly. The title kind of gives it away, doesn't it? So,
Yeah.
right now we rely on encryption that's based on really tough math problems, things that would take normal computers forever to crack. But with quantum computers on the horizon, with their, potential to just blaze through certain types of calculations, these systems that we depend on, they could suddenly become very vulnerable.
Yeah, exactly. I mean, that's the whole point, right? Quantum computers are just so much faster for certain calculations that they could potentially break the codes that we rely on today.
Yeah, it's a bit of an arms race, isn't it? So Schneppett's essay, I think it provides a really timely analysis of this, this emerging field of quantum communication and how it aims to kind of sidestep these vulnerabilities by, like we said, turning to the laws of physics themselves.
Yeah, and what we're going to do in this deep dive is try to really unpack the core ideas of quantum communication, how it's trying to build these like ultra secure channels, and what's the future of all of this.
Yeah, what are the practical implications?
Exactly.
So we're going to be looking at the nitty-gritty, the quantum mechanical principles, specific protocols like BB84 and E91, which we'll get into.
Yeah, those are fun.
We'll get to those, the real world challenges, and then sort of peer into the future a little bit.
Absolutely.
So think of this as a crash course, right? If you want to get up to speed quickly on this, like, really cutting-edge topic, why it matters to pretty much everyone in our, increasingly digital world, stick with us.
And it's not just hype either. This is real. This is the future.
No, this is happening.
Yeah, it's already happening.
Yes, so let's start by unpacking this whole quantum world a little bit.
Okay.
I think we need to talk about the fundamental differences between classical physics, which, we're all familiar with, and this quantum world when it comes to communication.
Right. So think about it this way. In classical physics, information is stored in bits, right? You have a 0 or a 1. That's it.
On or off, right? Like a light switch.
Exactly, like a light switch. But in the quantum world, things get a little weirder. We have these things called qubits. And a qubit, well, it can be in a superposition, which means, and here's where it gets strange, it could be both 0 and 1 at the same time until you actually measure it.
So it's not a definite thing. It's more like a probability cloud, a wave of potential.
Yeah, exactly. A wave of potential. And, Schneeppert gets a little into the math here. He uses this notation psi wrangle, alpha 0 wrangle plus beta 1 wrangle, which basically says, okay, this qubit, it has a certain probability of being a 0 when you measure it, and that probability is given by alpha 2, and a certain probability of being a 1 given by beta 2.
Okay, so it's not either. It's like a blend. Until the moment you look at it, then it snaps into one of the definite states.
Yeah, exactly. Like observing something can actually change what it is. That's quantum mechanics for you.
Right, and I think that brings us to another one of these like mind-bending quantum concepts, which is entanglement.
Oh yeah, entanglement, always a crowd pleaser.
Always a bit spooky.
Yeah, it's spooky action at a distance. That's what Einstein called it, and for good reason.
So in layman's terms, what's the core idea here?
Okay, so imagine you have two particles, could be photons, electrons, whatever, and you entangle them, which, is a whole other process. But now they're linked, like deeply linked, no matter how far apart you separate them.
Like they're tied by an invisible thread or something.
Yeah, something like that. And here's the kicker. If you measure one of the particles and find it, let's say, spinning up, you instantly know the other particle, even if it's light years away, is spinning down.
Even if there's no time for any signal to travel between them.
Exactly. That's the spooky part. It's like they're connected beyond space and time, which again is why Einstein wasn't a huge fan of this idea initially.
Right. But this is experimentally proven.
Oh, yeah, absolutely. It's one of the most well-tested aspects of quantum mechanics.
Okay, so you've got this entanglement where these particles are sort of mysteriously linked. And Schneeppert gives this example of cycle 1 squared up plus 11 wrangle, which I think illustrates this, right? It's like these two qubits they're in a superposition of both being 0 and both being 1 at the same time, but they're linked. So if one is found to be 1, the other instantly becomes the other.
Exactly. It's like they're two sides of the same coin, even when the coin is split in half,
Yeah.
and each half is on opposite sides of the universe.
It's a bit hard to wrap your head around, but it's crucial for certain types of quantum communication.
Absolutely. It's like the secret sauce, the quantum glue that holds everything together.
Right. So we've laid out some of the fundamental differences between classical and quantum physics. We've got superposition and entanglement. Now, how does all of this actually translate into creating more secure communication?
Okay, well, this is where we get into some of the really exciting stuff. So first of all, we have the no cloning theorem, which Schneeppert actually spends quite a bit of time on in his essay, and is really crucial for security.
Right. So what is this no cloning theorem all about?
It basically says that because of how quantum mechanics works, you can't perfectly copy an unknown quantum state.
Okay, so you're saying you can't just make a perfect Xerox copy of a qubit.
Yeah, you can't just hit Tro plus E, Tro plus V in the quantum world. It doesn't work that way. And the reason for this, and Schneeppert gets a bit technical here, is that quantum mechanics is linear, which essentially means that any attempt to copy an unknown state will inevitably introduce some disturbance, some error. You can't just perfectly replicate it.
So you can't just sneak a peek without leaving a trace.
Exactly. Any eavesdropper who tries to intercept and copy a qubit, they're going to leave fingerprints. They're going to mess with the original state, and that's what makes this so secure.
I see. So that's one layer of security.
Yeah, and then we have the measurement problem, which we already touched on a bit, and Schneeppert calls it mess problem in his essay.
Yeah, the mess problem, because it really does mess things up if you're trying to eavesdrop.
Right. So the whole idea is that in the quantum world, the act of measuring, the act of observing, actually changes the state of what you're measuring.
So you're saying, if I look at a qubit in a superposition, just by looking at it, I force it to choose either 0 or 1.
Yeah, exactly. That's the weird thing. By measuring it, you collapse the superposition, you force it into a definite state, and the original superposition, that wave of potential, it's gone.
So for an eavesdropper, this is bad news.
Oh yeah, because if they try to measure a qubit to see what information it carries, they're going to change it. And the intended recipient, let's say Bob, will know something's up when he measures it later.
So the very act of eavesdropping essentially corrupts the message.
Exactly. It's like a self-destructing message. If you try to read it without authorization, it blows up in your face.
Right. So it's a completely different paradigm compared to classical encryption, where it's all about mathematical difficulty.
Yeah, here it's about fundamental laws of physics. You can't outsmart the universe.
So to recap, we have these quantum properties like superposition, entanglement, no cloning, and the measurement problem. And all of these together are sort of the foundation for quantum communication and this idea of quantum cryptography and quantum key distribution, or QKD, which Schneeppert really dives into in his essay.
Yeah, that's the core of it. QKD is all about using these quantum principles to create a secret key that only the two communicating parties, Alice and Bob, know, and no one else can intercept without being detected.
Right. So it's not about sending the entire message securely. It's about establishing this shared secret key, which can then be used to encrypt and decrypt messages using classical methods.
Exactly. It's like a quantum handshake before you start talking.
Okay, so let's talk about why these QKD protocols are considered so secure. Schneeppert really emphasizes this point.
Well, it all comes down to those fundamental laws of physics that we talked about, right? The no cloning theorem that guarantees that an eavesdropper can't just make a copy of the quantum information carrying the key, and the measurement problem. That ensures that any attempt to peek at the qubits will introduce detectable errors.
So it's not about computational security, it's about this inherent physical security.
Exactly. Even with, hypothetically unlimited computing power, you can't break the laws of physics.
That's a comforting thought in a way, right?
Yeah, it's reassuring to know that there's a level of security that goes beyond just how fast your computer is.
So Schneeppert, he makes this very clear distinction between classical and quantum communication. Can we talk about the limitations of classical cryptography and why this quantum approach is seen as a potential solution?
Sure. So, as Schneeppert explains, most of the classical cryptographic systems that we use today, things like RSA or Diffie-Hellman, they're all based on these really hard math problems.
Yeah, like factoring huge numbers, right? Finding the prime factors.
Exactly. And these problems, they're really hard for normal computers to solve. It would take them, years, centuries, even longer to crack the codes.
But with quantum computers, that changes.
That's the thing. Quantum computers are specifically designed to tackle certain types of problems. And some of these problems, that are hard for classical computers, they're a piece of cake for quantum computers.
So they could just cut through these classical codes like butter.
Yeah, and Schneppet actually mentions Sir Shor's algorithm, which is a quantum algorithm that specifically targets these prime factorization problems that RSA relies on.
So once large-scale quantum computers become a reality, a lot of our current internet security just crumbles.
It's a real concern, and that's why this research into quantum communication is so vital. It's like a preemptive strike. We're trying to stay ahead of the curve.
So it's not just about, theoretical possibilities. This is about addressing a very real and potentially imminent threat.
Absolutely. It's about future-proofing our security.
Right, so we've talked about the advantages of quantum communication in terms of security, but Schneppet also mentions some other benefits. Can you elaborate on those?
Yeah, so beyond the security aspect, which is obviously huge, quantum mechanics opens up these entirely new ways of communicating, things that are just impossible with classical physics. And one of the examples that Schneppet highlights is quantum teleportation.
Yeah, that's something that always captures the imagination, right? Teleporting something from one place to another.
Yeah, it sounds like science fiction, but it's real, and it's been demonstrated in labs.
So how does it work, and how is it different from just sending a message really fast?
Okay, so in quantum teleportation, you're not actually physically moving the object. You're transferring the quantum state of that object to another location, and it relies on entanglement.
So you're sending information, not matter.
Exactly. You're sending the blueprint, the quantum blueprint, and it happens instantaneously.
So it sounds pretty complicated.
It is. It involves a lot of careful manipulation of qubits and measurements. But the key takeaway is that it allows for the transfer of quantum information over large distances without actually having to send the physical particle.
So potentially, this could be a way to build these super fast, super secure communication networks.
Absolutely. It's one of the building blocks of the quantum internet, which is this grand vision of a global network that uses quantum mechanics for all sorts of communication tasks.
Okay, we'll definitely come back to that. But before we get too carried away, I think it's important to talk about the challenges, right? Because there are still some significant hurdles to overcome before quantum communication becomes a widespread reality.
Oh, yeah, there are definitely challenges, and Schneppet is very upfront about those in his essay.
So what are the main obstacles that he identifies?
Well, first of all, the technology itself is really delicate. It's not easy to generate, manipulate, and measure these individual quantum states. It requires very specialized equipment and very controlled environments.
Right. It's not like you can just, whip up a quantum communication device in your garage.
No, not quite yet, at least. Although, who knows what the future holds.
So the technology is complex, and then there's the issue of noise, right?
Yeah, quantum systems are extremely sensitive to noise and interference from the environment, which can lead to errors and loss of information.
So it's like trying to have a whisper conversation in a crowded room. It's hard to get the message across clearly.
Yeah, and on top of that, we have this issue of distance. How far can we actually send these quantum signals reliably?
Because right now, it's pretty limited, right?
It is, especially with fiber optic cables. The signal strength degrades exponentially with distance.
And we can't just amplify the signal like we do with classical communication because of the no cloning theorem.
Exactly. We can't just make copies, so we need to find other ways to extend the reach of quantum communication, and that's where quantum repeaters come in, which Schneppet also discusses in his essay.
Yeah, repeaters are like these, relay stations that would boost the signal, but they're still very much in development, right?
They are. They're a very active area of research, but there's still a lot of technical challenges to overcome.
Right. So technology, noise, distance, and I think there's also the cost factor, right? Quantum communication is still very expensive.
Yeah, it's not exactly cheap right now, building these systems, maintaining them. It's all very resource intensive.
So it's not something that's going to be widely available overnight.
No, it'll probably start with, specialized applications, high security government, and financial communications, things like that.
Okay, so we've laid out the challenges, but let's get into the nitty-gritty of how these secure quantum keys are actually distributed. Schneppet spends a good chunk of his essay on QKD protocols, specifically BB84, which was one of the first and most important protocols.
Yeah, BB84, that's a classic, named after Charles Bennett and Jules Broussard, who proposed it back in 1984, hence the name.
So how does it work? Walk us through the steps.
Okay, so in BB84, we have Alice, who wants to send a secure key to Bob. And she starts by randomly generating a string of bits, zeros and ones.
Okay, so far so good.
Now here's the quantum part. She encodes each bit into a qubit, but she does this using two different and incompatible bases.
Bases, what does that mean?
Okay, so think of it like this. You have two ways of measuring the polarization of light. You can either measure it horizontally and vertically, or you can measure it diagonally. And these two ways of measuring, they're incompatible. You can't do both at the same time.
So it's like choosing which set of glasses to wear, polarized sunglasses or something.
Yeah, kind of like that. So Alice randomly chooses one of these bases for each bit, and then she encodes the bit as either a 0 or a 1 in that chosen basis, and then she sends these qubits to Bob.
Okay, so she's sending these qubits, but Bob doesn't know which basis she used for each one.
Exactly. That's the key. Bob now has to randomly choose a basis to measure each qubit, and he has a 50-50 chance of choosing the same basis that Alice used.
So it's like a guessing game. They have to be on the same wavelength, literally.
Yeah, and once Bob has measured all the qubits, he tells Alice publicly which basis he used for each measurement.
Okay, so they're communicating openly about the bases, but not the actual bits.
Right, and now Alice can tell Bob for which qubits he happened to choose the correct basis, the same one she used.
So they discard all the measurements where their bases didn't match.
Exactly, and the remaining bits where they both used the same basis, those form their raw key.
Okay, so they've managed to establish some shared information, but how does this actually help detect eavesdropping?
Well, here's the crucial part. If an eavesdropper, let's call her Eve, tries to intercept the qubits in transit, she has no way of knowing which basis Alice used for each qubit.
So she's just guessing, like Bob.
Yeah, and if she guesses wrong, and she's going to guess wrong half the time, she's going to mess up the state of the qubit because of the measurement problem.
Because she's collapsing the superposition without knowing which way it was supposed to collapse.
Exactly. And when Alice and Bob later compare a subset of their key bits, which are called test bits, they'll see a higher error rate than they would expect from just normal noise in the channel.
So a higher error rate means Eve has been snooping.
Exactly. It's like a burglar alarm going off.
And if that happens, they just throw away that key and start over.
Exactly. They don't risk using a compromised key.
And Schneppat also mentions these classical post-processing techniques, right? Like information reconciliation and privacy amplification.
Yeah, so even if there are some errors due to natural noise, Alice and Bob can use classical error correction codes to fix those. And then they use privacy amplification to make sure that even if Eve managed to get some partial information, the final key is still completely secure.
So they're essentially squeezing out any potential leakage.
Exactly. It's like making sure that the key is pure, untainted.
It's a very clever system, and it really highlights the power of these quantum principles.
Yeah, it's a beautiful example of how quantum mechanics can be used to solve real-world problems.
Now, Schneppat also discusses another QKD protocol, E91, which takes a different approach by utilizing entanglement.
Yeah, E91, developed by Arthur Akirkert back in 1991, it's a bit more mind-bending because it really leans into the weirdness of entanglement.
So how does it work? How do they use entanglement to generate a secret key?
Okay, so imagine we have a source that generates pairs of entangled qubits.
Okay, so we have these two particles that are linked.
Yeah, they're in this entangled state like we talked about before, where their fates are intertwined, and the source sends one qubit of each pair to Alice and the other to Bob.
So they each have one half of this entangled pair.
Exactly. And now they both independently choose a random direction to measure their qubit.
So they're not trying to guess each other's bases like in BB84?
No, it's a different approach. They're just randomly choosing a measurement setting.
And because the qubits are entangled, their measurement outcomes will be correlated.
Exactly. There will be a statistically significant correlation between their results, even though they made their measurement choices independently.
And how do they verify that these correlations are truly due to entanglement and not some trickery?
Well, they can use something called Bell's inequalities, which are these mathematical inequalities that are satisfied by any classical system, but are violated by entangled quantum systems.
So if their measurements violate Bell's inequalities, it's proof that they're dealing with genuine quantum entanglement.
Exactly, and that also means that there couldn't have been an eavesdropper, because if someone had tried to intercept the qubits, they would have broken the entanglement.
So the violation of Bell's inequalities is like a guarantee of security.
Yeah, it's like a seal of approval from the universe. Say, this is real entanglement, and no one has tampered with it.
Okay, so it's a different approach, but it still relies on these fundamental quantum properties.
Absolutely. And it has some advantages. It's potentially more robust against certain types of noise, and it can be used to establish entanglement over longer distances.
But Schneppat also mentions some challenges with E91, right?
Yeah, there's some practical hurdles. For example, Alice, Bob, and the source of the entangled pairs all need to be precisely synchronized.
Because entanglement is all about timing, right?
Yeah, the correlations only hold if they measure their qubits at the right time relative to each other.
And then there's the issue of decoherence, which we talked about before.
Right. Entangled states are even more fragile than single qubits. They're more prone to losing their coherence due to interactions with the environment.
So maintaining entanglement over long distances is tricky.
It is. And on top of that, generating these high-quality entangled pairs on demand is still a technological challenge.
Right, so both BB84 and E91, they offer these really compelling pathways towards secure key distribution, but they each come with their own set of technological hurdles.
Yeah, it's a constant back and forth between pushing the theoretical boundaries and figuring out how to actually implement these ideas in the real world.
Now, Schneepat also touches on some of the newer advancements in quantum cryptography, specifically device-independent QKD and continuous variable QKD. Can you explain what makes these newer approaches stand out?
Sure. So device-independent QKD, or DIQKD, it's a very clever approach that tries to get around the problem of trusting the devices that you're using.
Because in a way, they're always assuming that your equipment is working correctly, right?
Yeah, you have to trust that the manufacturer hasn't tampered with your devices, or that there are no hidden flaws that an eavesdropper could exploit.
So DIQKD tries to eliminate that trust.
Exactly. It says, okay, let's assume we don't know anything about the inner workings of these devices. Let's just treat them like black boxes. And the security is based entirely on the observed violation of Bell's inequalities.
So if Alice and Bob can see that their measurements are violating Bell's inequalities, they know their key is secure, regardless of what's going on inside the devices.
Exactly. It's like saying, we don't care how you did it, as long as the outcome is genuinely quantum, we're good.
It sounds very robust.
It is, theoretically, but it's also very demanding in terms of the quality of entanglement and the efficiency of the measurement, so it's still very much a research area.
Right, so it's a trade-off. Higher security guarantees, but more technological challenges.
Yeah, that's often the case with cutting-edge technology.
Now, what about continuous variable QKD, or CVQKD? How is that different?
So CVQKD, it's a different flavor of quantum key distribution that uses continuous properties of light waves, like their amplitude and phase, to encode information.
So instead of discrete qubits, you're using continuous variables.
Yeah, and this has some advantages. It's potentially more compatible with existing telecom infrastructure, which mostly uses continuous signals.
So it could be easier to integrate into existing networks.
Yeah, and it could also potentially achieve higher key rates and longer distances under certain conditions.
But there are also some drawbacks, right? Schnepp mentions some of those.
Yeah, the security analysis for CVQKD is generally more complex, and it can be more vulnerable to certain types of noise.
So it's a different set of trade-offs.
Exactly. Each approach has its strengths and weaknesses.
It's fascinating to see all these different strategies being explored. It's like a whole ecosystem of quantum cryptography is emerging.
Yeah, and it's a very active field. There's a lot of research and development going on.
Okay, so we've covered QKD protocols in quite a bit of detail, but Schneepat also discusses other applications of quantum communication beyond just key distribution. And we touched on this earlier, quantum teleportation.
Yeah, quantum teleportation, that's the one that always gets people excited.
It does sound pretty sci-fi.
It does, but as we mentioned, it's been experimentally demonstrated.
So can you walk us through how it actually works based on Schneepat's description?
Okay, so imagine Alice wants to send Bob a qubit, but she doesn't want to physically send the qubit itself because it might get lost or corrupted along the way.
Right, so she wants to teleport the information, the quantum state, not the physical particle.
Exactly. So the first thing they need is an entangled pair of qubits.
So they need to establish this quantum connection beforehand.
Yeah, it's like setting up a secure channel, and then Alice performs a joint measurement on the qubit she wants to teleport and her half of the entangled pair.
So she's measuring these two qubits together.
Yeah, and this measurement, it collapses the state of both qubits, but in a very specific way, and it gives Alice 2 bits of classical information.
So she gets 2 regular bits out of this quantum measurement.
Exactly. And she sends these 2 bits to Bob using a regular communication channel, like email or text message. It doesn't have to be secure.
Okay, so she's sending classical information, but what about the quantum state? How does that get transferred?
Well, here's the magic, Bob. Upon receiving these 2 bits, he knows exactly what operation to perform on his half of the entangled pair.
So he's essentially manipulating his qubit based on Alice's instructions.
Yeah, and by doing so, he reconstructs the original quantum state that Alice wanted to teleport.
So it's like she sent him a recipe, and he baked the qubit cake on his end.
Yeah, it's a very elegant process, and it really highlights the power of entanglement.
So it's not about sending matter faster than light, it's about transferring information instantaneously.
Exactly, and it has a lot of potential applications, not just for communication, but also for things like quantum computing and quantum sensing.
Now, Schneppat also discusses the challenge of transmitting quantum information over long distances, and he mentions the need for quantum repeaters. Can you explain why these repeaters are so important?
Sure, so as we mentioned before, one of the biggest obstacles for quantum communication is that these quantum signals, they tend to get lost or corrupted as they travel over long distances.
And because they're so fragile, they're easily disturbed by the environment.
Exactly. And unlike classical signals, we can't just amplify them because of the no cloning theorem.
Right, we can't just make copies.
So we need a different approach, and that's where quantum repeaters come in.
So what do these repeaters actually do?
Well, they essentially break up the long distance into shorter segments.
So instead of sending the quantum signal all the way in one go, you have these relay stations along the way.
Yeah, and each repeater station, it creates entanglement with the stations next to it.
So you have these chains of entangled qubits.
Exactly. And then they use a technique called entanglement swapping to connect these entangled segments together.
So it's like building a bridge of entanglement across the distance.
Yeah. And this allows them to effectively transmit quantum information over much longer distances than would be possible with direct transmission.
But building these repeaters is not easy, right? Schneppat mentions some of the technological requirements.
Yeah, there are a lot of challenges. For example, you need quantum memory,
Right.
which is a way to store quantum states for a period of time.
Because you need to hold on to the qubit while you're performing these entanglement swapping operations.
Exactly. And then you need really efficient single photon sources and detectors because you're working with individual photons and any loss can mess things up.
So minimizing loss is crucial.
Absolutely. And then you also need quantum error correction at each repeater station because these quantum states, they're always going to be subject to some noise and decoherence.
So you need to constantly correct for errors along the way.
Yeah, it's a very complex engineering task.
But if we can solve these challenges, the potential is huge, right?
Oh yeah, it opens up the possibility of building these vast quantum networks, spanning continents, even the globe.
Oh, and that leads us to Schneppat's vision of the quantum internet, this idea of a global network connecting quantum computers, sensors, and communication devices.
Yeah, the quantum internet, it's the ultimate goal. It's like the holy grail of quantum communication.
So what would this quantum internet actually look like? What would be the key features?
Well, first of all, it would be inherently secure because all the communication would be based on these quantum principles using QKD for secure key distribution.
So no more worrying about hackers breaking your encryption.
In theory, yes. And it would also allow for new types of applications like distributed quantum computing, where you could connect multiple quantum computers together to solve really complex problems.
And then there's quantum teleportation, which could be used to transfer data between different parts of the network instantaneously.
Exactly. It's like a quantum internet highway with data zipping around at the speed of entanglement.
But there are also some significant implementation challenges, right?
Oh, yeah. Building a quantum internet is a monumental task. It requires overcoming all the challenges that we've already talked about, like noise, decoherence, loss, the need for quantum repeaters, and then some.
So it's not something that's going to happen overnight.
No, it's going to take years, maybe decades of research and development.
But there are already some promising steps being taken. Schneppat mentions China's Metis satellite, which has demonstrated satellite-based quantum key distribution.
Yeah, that was a big milestone, showing that it's possible to do quantum communication from space.
So it's not just science fiction anymore, it's becoming a reality.
It is, and it's exciting to see how this field is progressing.
Okay, so in the final part of his essay, Schneppat shifts gears a bit and talks about the challenges and future perspective, and he focuses not just on the technological limitations, but also on the regulatory and ethical considerations, which I think are really important to discuss as well.
Absolutely. Technology doesn't exist in a vacuum. It has societal implications that we need to think carefully about.
So let's start with those technological hurdles. What are the main factors that are still limiting progress in the field?
Well, we already touched on some of them, like quantum noise and decoherence. Those are still major obstacles, and they're related to the fundamental fragility of quantum states.
Because these qubits, they're so easily disturbed by the environment.
Yeah, Any interaction with the outside world can cause them to lose their coherence, which basically means they lose their quantum properties and become useless for quantum communication.
And the typical timescales for decoherence are very short, right?
Yeah, we're talking nanoseconds, microseconds, which means you have a very limited time window to perform your quantum operations.
So it's a